Yeah. So are you able to see the screen?
Yes.
Yes.
Okay. So good evening, everybody. My name is Chandrima, and I am a PhD scholar in IIT Delhi. So I am a TA, teaching assistant for this course EMI or EMC and signal integrity, and the code whose code is E42. And yeah, so this is kind of a doubt clearing session, and obviously we will also solve some numericals. And if you guys have any doubt, or if you are having any difficulty in understanding the concepts or having difficulty in solving any problem, so I hope that I will be able to solve some of the problems and explain uh, how they are basically how you can solve them and how you can navigate through the course. Yeah, so I hope that are the course materials available to you? You can access them, the first week lectures and everything.
Yes.
Yes.
Okay. So I hope you have listened to the lectures. So in the introductory, could you, if you have any doubt, you unmute. Otherwise, please mute yourself. Okay. So basically, in the first week of this lecture, we have Professor Amitabha Bhattacharya, who is the course instructor. He has explained the basic concepts of EMI and EMC, right? Yeah, and before I start, one more thing. So, at any point of time, if you have any doubt, you interrupt me and ask me. Okay. Yeah. So, in the first week, we started with the course is obviously EMI and EMC. So, first we need to know what is EMI and what is EMC. EMI is what? EMI is electromagnetic interference and EMC is electromagnetic compatibility. And from the name itself, you can understand it talks about some kind of interference, electromagnetic interference. What does it mean? So, from very layman language, if we start to understand, so any kind of interference means you are suppose running something and some other signal is interfering with your system, right? That is called interference. Now, nowadays we are just surrounded by several types of electronic gadgets, right? You have your laptop, you have your PC, you have your mobile, tablets. Then you also have some other heavier machineries, like you have your washing machine, refrigerators, microwaves. So all these gadgets are some kind of source, and also at the same time they are receptor to electromagnetic the signals, right? All these electronic gadgets, they are residential gadgets. Then there are also like power plants, where like the transmission lines, the distribution system, they are also some kind of they are also source as well as receptors of this interference. Okay, so we are surrounded by uh, sources which can emit these signals, and they are also receptors to these signals, right? Now, site if in a particular space there are multiple devices and all of them are emitting some signals, if they are not electromagnetic compatible, their compatibility is not enough, they are not as per standards, then what will happen is they will go haywire, their operation will be not as desired, right? Suppose you are running your laptop and in the vicinity there is some device which is interfering with your laptop and it just goes haywire. Whatever you are doing, you are not able to do it. There is some disturbance. So that is not obviously desirable. We will not be able to do anything, right? So it is very important that these devices can work properly, even if there are other signals which are acting which are nearby. Okay. So in the lecture, like I will not go into detail because Professor Bhattacharya has already told that there are multiple uh, commissions and everything who basically decide the standards which we need to maintain. And whenever there is some product, okay, so there is Federal Commission, FCC in the USA, then there is IEC in Europe. There are various standards, okay. So whenever there is any commercial product that needs to go through some tests, some procedures, which will ensure that it is electromagnetic compatible. That means that it will not interfere, like whenever it is running, whenever it is operating, it will not interfere with uh, other devices, okay, or other machineries. It will not disrupt the operation, and of course it will not disrupt its own operation, and it will also be robust against other electromagnetic signals. Even if there is some emitter in the vicinity, it can operate as desired. It will not go haywire, okay. That is electromagnetic compatibility. So basically, even if there are disturbances, it will it can operate properly. It will not go bad. That is the point of EMC standards. Okay. Yeah. So there today what I will do is we will solve some problems, numerical problems, and if we get time, then actually I have listed down some problems. If there is time, we can do some more. Fine. And when I solve these problems, if you are having any difficulty, if you or any steps you are not understanding, just interrupt me and ask me. Okay, people are still joining, so I think I will wait a minute or two so that everybody joins and then I can start the numericals.
Good evening, ma'am. I have a doubt.
Ha, sure. Tell.
Yeah, in the lecture, actually, there sir explained one problem. So in that 2 alpha L log E is the formula. So in that formula, log E is given as 8.686 in the lecture. But in the calculator, while we are calculating, it is zero point 0.4 log E to the base 10.
Okay.
Actually, how can I send the picture? Actually, I have the screenshot of the problem,
Okay.
but I am
Just
unable to.
okay. Can you share your screen? I will stop sharing and you can share your screen. Is it okay?
Okay. Yeah, just a minute. Yeah, can you see my screen, madam?
Yeah, yeah. Just zoom it
So
a bit. Ha
so
ha.
it is power
Okay, fine.
loss dB, uh, 10 log 10 e power 2 alpha L. This is the formula.
Hmm.
So actually, log e to the base 10 was explained as 8.686. But in calculator, we are not able to get this value. I don't know how to do that in the calculator.
Okay. So log 10e, this part only there is confusion.
Yes, yes. How is that 8.686?
Okay, actually I haven't seen this part. Before that, can you please tell what sir covered in the first week's lecture? What are the
Yeah.
topics?
Uh, so basically, sir derived the equations. For example, there in the image you can see the cable, and
Hmm.
Z is equal to 0 to Z is equals to L impedance, and we derived the power loss, and we calculated dB microvolt to uh, watts. Sorry, volts. So these are the conversion formulas we have done,
Okay, okay.
and and signal analysis. Sir
So
derived the me.
did he start the Fourier analysis and all? Then the spectrums, Fourier spectrum.
Yes,
Then
it just two videos on that. On the in the initial stage it is. I think it will
okay.
continue in the next class as well.
Yeah, actually, okay, okay, fine. So today, actually, the problems I selected, they are mostly on Fourier spectrum and everything. So I was not aware that he started with the like this. The lecture started with this loss analysis and all. Okay, okay. From next day onwards, I will try to align with the lecture actually, because it may so happen that today what the problems I will solve, the sir has not yet reached till that point in his class.
Okay,
Okay,
madam. Okay.
fine. Okay, okay, fine. So just a second. So log. You were telling that this log 10, there is some confusion, right?
Yes, log 10 to the base. Sorry, log e to the base 10.
Huh.
In the class, it was explained as 8.686.
I think that there is some confusion. So if you just multiply 20 with log 10, I think this figure comes 8.68. So I think that multiplied by 20 thing will not be here. The total thing is 8.68. If
Okay,
you
okay.
right, if just do it, you will see it is coming some 8.68, something like that.
So the entire value 20 alpha L log e to the base 10. The
Yeah,
entire
yeah.
value is 8.686.
Right, right, right. Yes.
Okay, okay, okay. Thank you.
Okay. Okay. Yeah, so you
Hi,
can
ma'am. I have
unshare.
a question.
Yeah, tell. Huh,
That is Murali.
tell.
I'm attending this class, but I'm not in the India.
Okay.
Through online, do I able to take a examination?
Uh, I think as far as I know, like the examination is offline, but
Mhm.
this information we don't have. The TAs don't have these informations. What you can do is you can
Okay.
just mail the authorities. So if
Okay.
you have, you can just mail them and ask whether you can give the exam
If
online.
possible, yeah. If possible, you can able to put the authorities, corresponding authorities in the comment line so that I can contact with them.
Yeah, okay. Uh, so do you have any mail ID? Like, I think they must
Yeah.
have given you some contact information.
I like the last class I am not able to attend. I have just
Okay.
watched the video and I have enrolled for this.
Okay, so what I
Since
will do is, in the chat, are you able to see the chat? So I will just type hi. So in that case, I will
okay,
share the
yeah,
mail
yeah,
in the chat section. Like if I
yeah,
can
that will
get
be
the mail
fine
ID.
for me.
Okay,
Yeah, yeah,
okay.
that will be fine for me.
You can access the
And
chat, right?
uh,
Like of
have
this,
you sent the message?
I just sent a message. Are you able to see?
Okay. Once again, our notification. People, mm, no, I don't have. I'm not able to access the
Acha,
chat.
okay, no issues. So, okay, so fine. In the next class, I will just share the mail ID if I can get it. Okay, is
Okay,
it fine?
yeah, that will be fine. Is it fine? And the thing
Okay.
is like I have completed my BSc Electronics, that too in a distance, and I have completed my diploma in Electronic and Communication, and I
Hmm?
have a 10 plus years experience, and I'm in onsite. I am in onsite now. So,
Okay.
like, whether I am eligible to attend this class as per the qualification?
You have no, no, that is fine, but have you registered for this course? You have registered, right?
Yeah, I have registered, but in later in the time of the examination, I should not get any surprises. So that's why I just asked.
Uh, okay, so actually, the we also don't have like whether you are eligible or not, or whether you will be able to give the examination. These informations are not
Okay,
like we also don't know. So what our
okay,
job is basically just to conduct these sessions, doubt clearing sessions.
okay,
So
okay,
if you are in contact with some of your peers who are taking this course, you can also take help from them. So some of them must be like most of them must be in this country only. So if you
oh
are in
yes,
contact with any of them, you can just ask them to like they can give you those informations, I think,
Yeah,
okay.
up to
if
my
it is
Because
knowledge,
possible.
up to my knowledge, anyone can attend this exam. They need to,
okay,
before February 13th, they need to pay the fees, exam fees, 1,000 rupees.
okay,
And you
okay,
can select the slot, exam slot in your city, selected city. Actually, I am in Goa. So I
okay,
choose three locations in Goa for
okay,
exam. So for other
okay,
countries, I think in the NPTL website, you will be having email ID, NPTL email ID. So to that, if you
okay.
can mail them, they will reply you.
Thanks, Alok. I'm in France now, so I have checked that the same status. I have checked that because in all the cities in India they have given the centers, but in on-site it's not there. So that's why I don't know how to appear for the examination and proceed. And
Yeah, okay.
they
Okay,
mentioned,
can
and
we,
also they mentioned, yeah,
yeah, can we do one thing? Just, okay, I will just tell you my email ID. Whatever your queries are, you just list it down and mail me. So,
okay,
okay, so I will, then I think I will try to get the answers. Okay. So, because
yeah, it will be helpful for
now,
me. I just need a point of contact actually.
yeah, so, okay, you are,
Okay,
okay, you will not be okay. I will just write my mail ID. You can note it down. Just a sec.
okay, okay.
Can you see my screen?
Yes, I'm able to see.
Yeah. So this is my Gmail ID. You can
Okay,
send your queries here.
sure, sure, I'll do that.
Okay,
I'll
okay.
do that one.
Yeah. So, but yeah, the what so I mentioned earlier that we are also not like these informations. I also don't know. So I will try to get the answers. Otherwise, just I will request the rest of you. One of them, please help him so that he can like. About the examination and everything, just give him some confirmation so that
Yes.
okay, yeah,
Yeah,
just
thanks a lot for your support. Thanks, Alok, and thanks, man, for your
yeah,
support.
yeah, no problem, yeah, yeah. So I think uh, we can start the session. So first few questions are just theoretical. So at which the first question is at which frequency does the infrared rays start? So in the beginning of the lecture, I think sir showed you one diagram where the spectrum, the electromagnetic spectrum is shown. there are various kinds of electromagnetic rays signals, like starting from radio frequency, then microwaves, then infrared, then UV, then gamma ray, X-ray. All these things were listed. So if you just refer to that diagram, you will be able to see that the first option is correct. From 1000 gigahertz, the infrared starts. Okay, people are still joining. Okay, so this is the diagram basically. So here, if you see, the frequency is given. So at the radio frequency is 10 power 4, which is basically what? 10 kilohertz. Then humans, then microwave, infrared. Infrared is 10 to the power 12. So 1000 gigahertz. Then we have the visible light. Then we have UV, finally X-ray, and at last we have gamma rays, which basically emit from the nuclear fission or fusion reactions. Okay. Some are from natural sources and some are from human interference, like the nuclear projects, all these nuclear, yeah. So then next question is, which of the following has highest effect at low frequencies? Okay. First is EMI. EMI is like this is the generalized one, electromagnetic interference. It doesn't tell us anything about low frequency or high frequency. EMI covers the whole spectrum. Then we have NEMP, so nuclear electromagnetic pulse. Okay. Then we have LEMP, lightning electromagnetic pulse. Then HPM, high power. Uh, so I think the correct option is LEMP. Yeah. So lightning electromagnetic pulse that has the highest effect at low frequencies. Okay. So LEMP basically this is a natural phenomena. Lightning. Whenever there is lightning, it emits some electromagnetic uh, emissions. Okay. Yeah. Then the third question. A system is electromagnetically compatible if it does not interfere with other systems, it is susceptible to emissions from other systems, it does not cause interference with itself. Obviously, the first one, it does not interfere with other systems. One of the fundamental clauses of electromagnetic compatibility is it must not interfere with other systems, and even if it interferes, the interference should be below a limit. Limits are specified everywhere. If you see the standards, so sometimes you just go to the net and you can just see the standards. Okay, so everywhere there is a limit, specified limit. So you will have to comply with those limits. Unless if you can't comply with those limits, your product can't be commercialized. You may have the best design in the world. You may have like very compact, very efficient design. But if it doesn't comply with the EMI, EMC protocols, then it is useless. You can't use it. You can't put it in the market. Okay, that is the problem.
I have a question here now.
Yeah, ask.
Uh, like previously, we have developed a product and we have sent it for the CE certification for the
Okay.
EMI EMC, also the TUV and EMI EMC. So in
Hmm.
that one, they are asking what we did is like it's like out of Zigbee protocol product. And what we did is we have increased our ground path, both the digital and analog ground path in a very strong manner. Uh, as of my knowledge, we did that very strong ground path, and it complies the certification. We got the certification.
Okay.
So, like
Okay.
in all the cases, only the ground path, in increasing the ground path will support, or do you need to do any other fine tuning for the product?
Uh, yeah. So what is your product like? Can you say like, or is this confidential? What kind of product?
No, no, no. I can give the generalized thing. This
Okay.
is
Okay.
like Zigbee over the air network. We are able to establish the device communication.
Okay.
And
Okay.
the thing is, like we are using IR as well. If the Zigbee fails, for example, in the worst case scenario, Zigbee fails, IR will work and to control it. That is the thing. So in that one, because I was in the TV compliance while doing the testing. So in that one, they are having two electrodes, which is comes near with a high voltage, which comes near the device. So they will check whether the ground is even if the device observes the high voltage and it's grounded properly. It should not affect the. It should not affect the device. It should not burn out the device. It should not damage the device.
Hmm.
So that is what we did. So only thing is we are very closely looking to that damaging of the. Uh, but in other frequency ranges, we didn't detect. So I just want to know how to mitigate, because with the ground path increase as well, it was okay.
Hmm.
But for the frequency, when the high voltage electrodes are placed nearby, how the frequency test we can able to do?
Yeah. So actually, so I guess you have like you are in industry for how many years? Like I think for uh
For a specific industry for 9 years exactly. If you are
yeah. So I think you have like in terms of tactical knowledge, you are far more, you know, much better than me actually. So I am not aware of the like exact industry protocols, how the tests are done, or like inter specifically for EMI EMC, I am not very knowledgeable about all these things. How what are the exact test procedures, or what are the exact like how you do the radiated emission or conducted emission. So I am not aware. You will be like you are much more experienced than me, I guess. So, but yeah, I mean, see, basically what happens is in the when you are operating at very high frequency in like hundreds of megahertz or something in gigahertz or like that, in that case the parasitics come into play, right? So if you have some circuit, I am working currently in the power electronics domain, so I can tell you in that perspective. So basically if you suppose have a power electronic circuit, right? Now in if you are operating in very low frequency region, this is okay. But nowadays obviously we do high frequency pulse width modulation, right? So when you do pulse width modulation, and now we are also we are also heading towards wireless power transfer, right? WPT, I don't know whether you are familiar with this term, wireless power transfer. So uh, like you must have heard, right? Wireless charging, all these things in the mobiles nowadays. We have wireless charging,
yes,
all
yes,
these
right,
provisions, right? They are all done
yes,
by
right.
these WPT setups. Okay, mostly inductive WPT, inductive wireless power transfer. Now what like if suppose all those if you talk about capacitive wireless power transfer, CWPT, in those case we use GAN devices. Okay, gallium nitride devices we use, and they are operated in a few the operating frequencies suppose between 6 to 7 megahertz usually. Okay, the switches turn on and off at this frequency. Now you can understand that at this kind of frequency the parasitics play a very important role. There will be parasitic capacitances. there will be parasitic inductances. Okay. And what we can do is, so what is the basic schematic? There is one emitter that will emit some electromagnetic signals, okay, disturbances. So, okay, so this is the emitter. Then there is a coupling path and there is receptor, which is getting affected due to those emissions. Okay, there is transmitter, there is receiver, and there is this coupling path, some form of coupling. And most of the cases, if we talk about conductive emissions, there are the parasitics come into play. This there is some parasitic capacitance to the ground, okay, like this. So one way to reduce this interferences is to make this path very inefficient. So every signal needs some closed path, right? Every signal, so electromagnetic signal, they need, so electrical signals, obviously, they need some closed path. So from the path from where these signals will flow, you will have to make them so inefficient that even though there is some form of interference, it is very weak. It can't affect the operation of your system. Okay. So for that, the grounding and all those things should be very robust. Those things should be very proper. Okay. And this is for conducted emission, I am saying. And there is also radiated emission. What is conducted emission? Which we can capture. So the signals flow through the wires of your system. There will be some wires. So they will flow. And radiated emission is, you can obviously understand, that is through radiation. That is more difficult to capture, or that is more difficult to measure in terms of measurement also, and in terms of mitigation also. This is more difficult than conducted emission. Here you can use EMI filters. Most of the cases we use some filters, okay, to mitigate these effects. But for radiated emissions, it is more difficult. So yeah, so there are different procedures by which you can pass those tests. But I think you are more aware of those tests. I am not actually aware what are the procedures that are done in industry. Okay. So one day I think you can just tell about, like like in generalized way, like what are the tests and how do you do it. Like I will also like to know, because I am not very knowledgeable about that.
Sure, sure. I will do that.
Yeah, yeah.
Yeah.
Okay.
Thank you.
Okay.
So,
Ma'am, I have
one last question.
regarding.
Excuse
Yeah.
me. Like, for example, it's a conductive testing. Yes, we do have. Another one is non-conductive testing, which is like emitted by some devices. So,
Hmm.
like, what we do is like that time, the different kind of snippers, different frequency snippers, we will create it. So
Hmm.
we'll find, because like one sniffer, it is the bandwidth is between the 1 GHz or something. It will sniff the signal only between that signal, not
Okay.
more than that
Okay.
or not like that. So we'll
Okay.
create multiple levels of snippers, and we'll identify where exactly the
So
emission is
there will be
started.
some quasi peaks, right? So the spectral analyzer will give you
Yeah,
some peaks.
spectrum analyzer, exactly. So
Yeah, yeah.
we'll create, you'll interface with the attenuators matched with that one. For
Hmm.
example, one scenario I can tell you,
Hmm.
like once by mistake, we should not take any mobile phones inside, but once
Right.
we
Right.
taken it, but with that one, we can able to find out, and with the spectrum analyzer, we identified there is some Vodafone mobile, some was which is nearby. Then we identified,
Okay.
yes, there was a mobile like that. So we,
Okay. Okay.
for that non-interference emissions, we have to create a multiple snipping, and we have to identify, and because wireless is not visible, right, so it's very difficult to identify, but we can create the multiple sniffing setups for that.
Okay. Okay. Acha, acha.
Okay.
Yeah. Yeah,
Yeah.
obviously, because like I will tell you. So when I work on the power electronic circuits, sometimes what happens is like, suppose I am running my setup, and somebody else just adjacent to my table is also running her setup or his setup, and she just turns on some voltage source or some some emulator or something, then my system gets disrupted. Okay, that is a clear sign of EMI. So the moment she turns on, my waveforms get distorted. Okay, so we have seen that in lab, but obviously in lab that is very what should I say, very crude form of testing. But in industry the tests are more stringent, right? Because you will have to actually make something out of it, and you will have to sell it. So the test procedures are more stringent and more thorough. But yeah, like in everyday life you will be able to see it there, like it is very common actually. And if you have seen the lecture, you must have seen that sir has listed down multiple catastrophic events which happened due to the this EMI issue, right? So people earlier couldn't identify why this happened, but after that it was identified that this was because EMI. Okay, so this is a very like what should I say, like very important aspect of any electronic component.
Okay. Yeah.
Okay, so okay, we will just get
Good
back to
evening,
the
ma'am.
problems then. Yeah, yeah. Okay.
I want to
Some.
ask something. So
Okay. Ask.
I'm I am new to this field, so I just want to ask whether this course include introduction to various tests that are being performed under EMI EMC.
Yeah. So
So
what
basically,
huh,
I want you to brief this course ki what will be the various component of this course.
yeah. So yeah. Actually, what I could understand is the mostly the course will be on the theoretical aspect. Okay. So there will be obviously some practical aspects. So there is one instrument called LISN, okay, line impedance stabilization network. So the basic things will be covered, like what are the instruments we usually use for measuring this EMI, and then what are the instruments, so basics of them. And along with that, mostly there will be numericals. Today also, if you see, if you have seen the lectures, there are Fourier analysis, then spectrum, uh, all
Yes,
this, the harmonic analysis, all these things are there. So mostly it will be theoretical. Do you have like are you aware of this Fourier analysis, then all these things, have you heard of
yes,
them?
yes. I am aware of it, ma'am. That is what I want to ask you. What is the utility of these numerical in the industry with respect to the EMI EMC?
Industry, see, in the industry, if I'm being honest, in the industry people are not always doing, like they are not solving Fourier analysis and then doing the tests, obviously. But when you are doing some course, you will have to also know the theoretical aspects, right? So
But ma'am, what I believe is this course is designed for the purpose of skill enhancement. Don't
yeah,
you think so?
yeah. So but I can't, like, see, I have not designed the course, right? So I don't have that independence that I will do whatever I want. Or so the course has already been designed and the course contents are also predefined. What I am here for is just to like solve the like solve some problems, and whatever is in the course I can just add some part of it. I am not allowed to do like some addition from my own. I hope you
Okay,
understand,
okay,
right?
okay.
So I am
Yes,
not the
yes, I
course
got your point. Thank
instructor.
you, ma'am.
Yeah, I am not the course instructor. I am just a teaching assistant. So whatever is this in the content, I will just have to follow that.
Okay, ma'am, I got your point.
Yeah, yeah. Okay. Okay, so yeah, so we will get back to the problems.
One small question regarding the previous question which was shown.
Previous
Yeah.
question, this one?
Yeah, just would like to know, generally what we are seeing here is like different phenomena, but how do we connect it with the highest effect severity? Is it like in terms of the pulse duration or what? Because in the lecture slide, we could see one consolidated single slide wherein the waveform of NEMP, waveform of LEMP, HPM were shown together. So is that related to the severity? How do we connect to this?
Yeah, so I think if you have seen, the rise times were shown for the different pulses. So in time domain, so time
Yes.
domain waveforms were shown. So yeah, like the rise time basically defines this effect.
Lifetime is related to the frequency, right, ma'am? If it is shorter, so we will be
Yeah,
having a higher frequency impact, right?
yeah,
Okay,
yes,
so
yes.
whether this LEMP, the answer is LEMP, right? So in this case, LEMP has a tapered slope rather than a steep slope. Is it so when compared to the other
No, but
pulses?
it is at low frequency. So like it basically there was this spectrum, right? From low frequency towards high frequencies. So
Correct.
LEMP comes under towards the lower frequency range. And towards the higher frequency range, all these nuclear weapons, nuclear uh, emissions, all these things comes in the higher frequency band, obviously, because you can understand the gamma, the nuclear fusion, fission, all these things occur at very high frequencies. And this lightning comes basically, but that doesn't have to define its effect, like its what should I say, it doesn't define its how much catastrophe it can cause. Okay, so this only just defines what is the frequency spectrum. At low frequencies means it is situated at the lower frequency spectrum. Okay, so towards the radio like you can understand, right, what I am trying to say. So
My simple question, ma'am, just I'm also learning, so that's why I'm asking. Not
hmm,
even specific to this phenomenon. So I just want
hmm,
to understand like the difference. So which causes the how does the rise time impact? Rather, that can be considered as a question. Rise time, if for example all these pulses have different rise times, so
yes.
that decides the frequency at which this phenomenon happen, low frequency or high frequency, like you said, gamma or microwave, or does it, is it the criteria?
Yeah, yeah, obviously, because so see the frequency spectrum means that, yeah, obviously this pulse, whatever pulse is this, okay, so one pulse would have multiple frequency components, right? So one waveform will have, so that we will have to analyze that what are the frequency components. Okay, so based on that we can comment on that in the Fourier. So in this course you have done Fourier analysis, right? In the Fourier analysis there will be, suppose some any irregular, some any shape of waveforms, any shape you can take, and then you will have to analyze what are the frequency components, right?
Okay.
So there will be one fundamental, whenever there is an irregular shape. Okay, so we can, what do we do in Fourier analysis? What we do is we just represent one waveform which is irregular. We can represent it in terms of sines and cosines. There is one fundamental frequency omega naught, and then it has some multiples of omega naught, maybe 2 omega naught. It may also have 3 omega naught, 5 omega naught, based on the shape. Okay, so from that we just get what are the frequency components that these waveforms have. Okay, But
Alright.
yeah, like okay, I will just okay, I will see the question also. I will just see it once more myself, and I will try to explain it more clearly. Okay, just okay, I will remember this one. So your question was how exactly the rise time is related to your effect, right? How the rise time uh, just we
Yeah.
can
Yes, I
relate
can
it.
reiterate, ma'am. Like lightning pulse has been shown to be the having the highest effect at low frequency. So we are able
Yes,
to see the time domain pulse for that. So
yes.
how does the time domain pulse related to this effect, severity at low frequency?
Yeah, 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 yeah. Okay, okay.
Right. Thank you.
So we were discussing question number 3. So the answer will be so it does not interfere with other systems, then it is susceptible to emissions from other systems. It does not cause interference with itself. So 1 and 3, right? If it is it should not be susceptible to emissions from other systems. So this is wrong. 1 and 3, they are right. And then question number 3, this diagram I think you have already seen. Uh, this shows the different types of emissions. First is the radiated emission. So the emissions are occurring by radiation. Okay, it is radiation. So this one is right. Then radiated susceptibility. So now for the emission, so this is the source and it is radiating emissions. This is the source. Okay, these are the source. And due to the emissions from this source, other equipments may get affected. And what is radiated susceptibility? That your equipment is getting affected by other sources. That is susceptibility. So this representation is also correct. Third one is conducted emission. So this is a potentially susceptible component. Okay, so this is susceptible to emissions, and some emission is coming through via this conductor. So this is not emission, this is susceptibility. Okay, so they should be interchanged. This should come here and this should come here. This is conduction and this is susceptibility. So the correct answer is C, 1 and 2. Okay. Okay. Now we have come to the part where we will have to actually solve some numerical. What it is saying, consider a trapezoidal pulse governed by the equation, determine the value of C naught. This has already been discussed in the lecture. What is the time domain equation? So xt is equal to at by tau between this interval and then a in this interval. First, this is a ramp till t is equal to tau, right? T is equal to tau from 0. Then it is equal to a. So this is equal to a and it gets repeated like this. It gets repeated. Time period is capital T and the values are given: a equal to 1 volt, tau equal to 1 second, capital T equal to 2 second. What is the value of C naught? C naught is what? C naught is nothing but the average value of any signal. In Fourier analysis, you have C naught and then you have Cn. Okay, C naught is the average value. And how can we find the average value? By performing this mathematical operation, right? I think you already know how to do it. So there will be xt dt, Okay. This is the mathematical formula. And by this, you can find out what is C naught. So here, this was covered in the lecture itself actually. So if you just perform this integration from 0 to tau, there is this ramp, that is at by tau dt, and then from tau to t it is constant. It is constant at a value a. Okay, so a dt. And if you will just have to perform this integration and replace t by tau. Okay, then you will get this expression a times 1 minus tau by 2t. We already know what is the value of a, what is tau, and what is capital T. Then you can easily find out. So 1, this was 1 volt. Then 1 minus tau was 1 second, and it was, I think, 2 second, right? So 1 by 4. So it comes out to be 3 by 4, right? So option C here. So is it okay? This is a connected question. So determine the value of the second harmonics. The waveform is same. What we need to do is determine the value of second harmonic. The value here means, so whenever you will find out any harmonic, there are two parts. There is the magnitude and then there is the phase angle. So there are always two parts. If they specifically say magnitude, then you will have to only find out the magnitude. And if they say phase angle, then you will have to find the phase angle. And if just the value of the harmonic, then both of them, magnitude as well as the phase angle. Okay. So for this, what we need to do is we will have to find out Cn, right? How we can find out Cn? So this is 1 by T again, then T1. T1 may be any instant, any random instant, because this is a periodic waveform. So we will have to consider one complete period, T1 to T1 plus T, then xt e to the power minus j in omega naught t dt, right? I have already solved it in my copy because we will not get time to derive it completely. You will be able to do this integration, right? This will be there will come integration by parts also. So if you just do 0 to tau, then this is at by tau, then e to the power minus j in omega naught t dt. Okay. Then this is in this interval 0 to tau. After that, we have the interval tau to capital T, where the value is a. A times e to the power minus j in omega naught t dt. Okay. So this we will have to perform integration by parts. And this one is simple. Okay. So the final expression you can just confirm by deriving it by yourselves. I will write the expression, the final expression. Okay, so that is ja by 2 pi n 2 pi n, then 1 minus e to the power minus j n pi to tau by t sine c n omega naught tau by 2. Okay. Just try it by yourself. If there is any problem, you can tell me in the next session. Right. So n is what? N is the order of the harmonic. Here we are supposed to find out the second harmonic. So n equal to 2. If it would have been third harmonic, then n equal to 3, like that. Okay. This is the order of the harmonic. We will replace n by 2. And what is tau by t? Tau by t is tau is 1 second and t is 2 seconds. So tau by t is equal to half. Okay, 0.5. 0.5. Just replace these values. What we will get is, I will write here. Okay. The final expression would be then ja by 4 pi 1 minus e to the power, so n 2 pi and this is half, so minus j pi and sine c is what? Nothing but sine n omega naught tau by 2 by n omega naught tau by 2, right? Now n is equal to 2 omega naught is 2 pi by t. Omega naught is the angular frequency of the fundamental. So 2 pi by t and tau by 2. Tau by 2. 1 2 gets this 2 gets cancelled, then and tau by t is again half. So this is pi. Sine pi by again in omega naught tau by 2. So here also we have pi. Right. Sine pi is equal to 0. So this whole thing becomes 0. And we have what we have? Ja by 4 pi. Simply this remains. And as we have j, therefore you can understand readily that the angle will be 90 degree because we have j over here. A is equal to 1 volt and 4 pi. So 1 by 4 pi is the magnitude, right? What does it come as? So 1 by 4 pi, if you do, you will find that the magnitude is this one. Okay, option B. This is the correct answer. Okay, is it okay?
And these slides and annotations will be available for us.
Yeah, these documents will be available. I will share the link. Actually, they from NPTEL, they will share the link. This link and the video will also be available in YouTube. Okay.
Okay. There is a section in the app which we are able to see problem solving session. So
Yeah,
along with
that
it,
only.
so in
That
that it will be
only.
uploaded. Huh?
Yeah, that these documents will be uploaded and also the videos will be accessible.
Okay.
Okay. Huh. So what I will suggest is you just try to like this integrations and all you try to do, okay, because in exam also or in the assignments you will have to solve similar kinds of problems. So you should be very adept to solving these things. Okay. We will go to the next problem. The same problem, but now we have to find out one-sided spectral expansion coefficient. So in this first lecture, did sir cover this one-sided spectral expansion?
Yes, yes.
Okay, okay, okay. Yeah. So what is one-sided spectral expansion? It is nothing. So basically, if you sorry, just a minute. Hmm. It is suppose one signal is we can expand it from minus infinity to plus infinity. We can simply represent it from in the positive half. Okay, so from basically n equal to 1 to n equal to infinity. That's why it is called one-sided. You can simply represent a signal by shifting it to only one side of the spectrum. Okay, so that's why this is one-side spectrum. We have already seen how we can find out Cn. Okay, C naught also we have found out, Cn also we have found out. And based on what is the n, we can find out the exact magnitude and phase angle. What is Cn plus? Cn plus is the positive side coefficient when you consider n equal to 1 to infinity, not n equal to minus infinity to plus infinity. Okay, this is just in one side. So this is basically 2 times Cn. Okay. The derivations are given in the lecture series. So you can just refer to the derivation. So this is 2 times Cn. Now what they have asked C3 plus, that is third harmonic component. Okay. Third harmonic component. What was the generalized expression? The generalized expression was, so I wrote it earlier, Ja by 2 pi n. Okay. Ja by 2 pi n 1 minus e to the power minus j n pi into tau by t, then sine c n omega naught tau by 2. Okay. Why this is? Because we have the same waveform. If these expressions would have been different instead of this, then obviously the expression will also change. Okay, this is only for this trapezoidal waveform that we saw, right? For this waveform. If we have some other waveform with some different shape, then the expressions will change. Now for fifth harmonic, for third harmonic, we will have to see, right? This remains the same, Ja, and now n is equal to 3, so 6 pi here, 1 minus e to the power, this becomes j 3 pi by 2, j 3 pi by 2, and sine c 3 pi by 2, okay? So can you guys also calculate and tell what is the magnitude and phase angle? You guys can also calculate and tell, okay? Just try to, this is very simple. E to the power minus, this is what we know, right? E to the power j theta. How we can write it? We can write it as cos theta plus j sin theta. Okay. This is how we represent a phasor, right? E to the power j theta. And e to the power minus j theta is cos theta minus j sin theta. Okay. If we write e to the power minus j 3 pi by 2, so cos 3 pi by 2 is equal to 0, and minus j sin 3 pi by 2. Sin 3 pi by 2 is what? Sin 3 pi by 2 is equal to minus 1, right? So minus 1, this becomes only j. So we can just so this is just so it was ja by 6 pi, then 1 plus j was sine 3 pi by 2 by 3 pi by 2. Okay. 3 pi by 2. So can any of you tell the answer? What will be this?
It is 0.18, sorry, 0.1084.
Yeah, but I think only this one will come 0.05 something. But while as you were considering one-sided spectral expansion, then it will have to be multiplied by 2. Okay, for C3 plus. Then you will get the final answer. Okay. But only this portion, I think it will come some 0.0542 like that. Okay. So for one-sided expansion, we have to multiply it by 2, then you will get 0.1084 and the angle will be 78.02 degree. You know, right, how to calculate this phase angle. So this is in like rectangular Cartesian format. Okay, so what we will do is, there we have j, and here you will get something like 1 minus j 0.212, like that. I think this only I got 0.212, and outside it has j by a is 1 volt, so j by 6 pi. Okay, if you just represent it in as magnitude m and angle some angle, then you will get the magnitude as 0.1084 and the angle as 78.02. What will be the angle here? J means 90 degree. Okay, 90 degree, and this angle, if you do tan inverse minus 0.212, this is some 11 point some degree. Okay, so this gives us 78.02 degree. You can do it by yourselves and check. Okay, I did it in my copy, and I think these are the figures that I got. Fine. Okay. Yeah. So next question. Consider a periodic waveform defined by xt equal to a during this interval and 0 during this interval, and the values are given. Determine the value of C1n and 1. This is the fundamental component, right? C1. The waveform is very simple. You have a pulse waveform. From 0 to tau, it is A, and for rest of the period, it is 0. This is xt. xt. Okay. And this continues. This continues. Okay. Now we will have to find out what is C1. C1 you can find out by using the same expression that we were using earlier for the third harmonic, for the second harmonic. The same expression you can use and you will find out. Okay. Ja by 2 pi n and then sine c in omega naught tau by 2. Right? Tau by t is half. This is 1. So j pi by 2. Okay. This is minus j pi by 2. And then sine pi by t tau by 2. N equal to 1. Okay. So this is again pi by 2. Okay. So what we have, this is the expression. So J by 2 pi over here, and then 1 minus e to the power minus j pi by 2 and sine c pi by 2. Okay. Here the correct answer would be 0.5 hertz. Okay.
Madam, what is that bracket one above C?
Which one are you saying?
Determine the value of C1n
Uh,
to the power of bracket 1. What is that bracket 1?
so the bracket one is
C1 is the fundamental component.
hmm, hmm, hmm.
Bracket 1 is also, that means fundamental value. Fundamental.
Yeah, I think so. Yeah, maybe. I'm not sure why. C1 and maybe I don't know. Like this is not one-sided. So determine the value of C1 and yeah. So from like you can just solve this and check what is the magnitude, okay, of C1. What value are you getting? Can you just check from this one? Okay, so just give, I will take a break of 5 minutes, okay? In the meantime, you just solve this. So I will have to make a call. Okay, I will get back to you after 5 minutes, okay?
Okay, ma'am. No issues.
let's resume. So one of you were asking what is the significance of this one. So this is basically the first order approximation of this Fourier expansion. I think today the problems I took, they were like from the core, the course content is a bit, there is a bit of a deviation. So from the last year's course, so that's why I think this part is not yet covered. So I shall again take this problem in the next session. Okay. Yeah.
Okay, fine.
Yeah. So this problem is again kind of a repetition. You have to calculate Cn for the sixth harmonic. Okay. And all these values are given. So simply just replace the values in the expression of Cn. Okay. Think we have derived it multiple times. So you just solve it by yourselves. That way you will be able to practice. Just use this formula. Yeah. So I have written it. Just use this formula. Replace the values of capital A, then N, and all these things, and you will be able to find out what is the value of the sixth harmonic. Okay. Just yeah. So did you get the answer? What are you getting?
Madam, are you sharing your screen?
Yeah, okay. Did it go away? Just okay. Just a minute. Okay. So did you find out what will be the value of Cn? Yeah, but one thing, just okay. Okay, so actually here you can't, this is not right actually what I wrote, because here the waveform is different. Actually, I was considering the previous waveform, which was this. So now this is not the waveform. The waveform is this, right? So first this is A, then this is 0. So till the point tau it is A, then this is 0. So this generalized expression was for this kind of waveform. But here it will be a bit different. It will not be this. So here Cn is, you can simply find out. So this is easier than the previous one. So just if you just perform this integration from 0 to tau, this is A. So A e to the power minus j in omega naught t. Okay. And rest of the part it is 0. So we don't have to consider it. The expression will be A tau by t sine in omega naught tau by 2 by n omega naught tau by 2. Okay. This is after many manipulating the expression. Okay. So you don't have to always remember this expression. You can just your own way remember it. This is just because this sine C, all these things, these are like just for making it simpler. But you can simply just do it and replace the values a tau and everything. Okay, you don't have to remember this. If there is time, you can simply just remember this expression and find out what is the result of the integration. Okay, because it is not always possible to remember the expressions for all the waveforms. So just simply this is the basic formula, okay, for any kind of expression. So instead of a, there will be some other thing. Here you will have to place the xt expression as xt is equal to a. So I have replaced it with a. But if there is some other thing, this may be at by tau, as we saw earlier. There may be some other expression at square or a any function of time. Okay, any function of t, you will have to replace it. So just remember the generalized expression. Okay. So here if you put all the values, you will get 0. Okay, that will be the value of Cn for sixth harmonic. It is 0 because this sine n omega naught tau by 2, this comes out to be 2 pi, and sine 2 pi is equal to 0, so you will get 0. Okay. Fine.
Okay, madam. Ma'am, is there any negative marking in the exam?
Negative marking. I don't think
If
so.
there is any wrong option, like gate exam, will there be any negative marking?
Uh, I'm not sure actually, but I don't think here negative marking they do. But still, you confirm it, okay? Actually, like they don't give us any information about the exams and anything. So actually, that's why I'm sorry, but I don't know all these informations. So
Okay,
just
okay, madam.
confirm it from them. Okay, just mail them and ask. Okay, so today I think I will stop here, and in the next week we can meet in the same time. And if you have any doubt or you have any suggestion, like if we can add something else or some solve some different problems or anything, just let me know. Okay.
Ma'am, are
Sure,
you
sure.
working in electric vehicle charging infrastructure design?
Yeah, kind of. Yeah, like that. Yes.
So actually, I am also working in the same area in PhD in NIT Goa.
Okay.
So actually, I have a coursework in the first semester, so I registered for NPTL.
Uh-huh.
So are you applying this EMI EMC for that research, uh, for that charger analysis?
Yeah, I will tell you what is the thing. Actually, what I basically work on is the converter design. Okay. For
Okay,
EVs, EV chargers, onboard chargers, I basically design like PFC converters and all these things, isolated DC-DC converters. But the point is, this EMI, EMC, these issues in our laboratory, they are not like, if you even if you see, this course is a very specialized course. If you see normal curriculum, you will not find any course particularly on EMI or EMC.
okay,
So I myself didn't do any course on EMI or EMC, but this is a very important issue. If you were suppose targeting to make a product, suppose you have done multiple iterations of a design of a converter design and you want to make it a product, right?
okay,
So in that case, EMI and EMC will play an important role, right?
okay,
But in our laboratories, actually, uh, in the labs, you will be able to run the converter even without designing any EMI or EMC filter sometimes, because in laboratory this is an enclosed space. There are very few instruments. Okay, so this may not be a problem, but in actual scenario, EMI and EMC you will have to you will have to analyze all those things.
okay,
So I also don't have very vast experience in this area, I would say, because
okay, ma'am.
yeah. So
This
but
is
yeah,
actually
huh.
recently trending, this topic.
Yeah, I won't say recently, because all the commercial products they always go through this process. So whatever electronic device you use, they will have to go through these test procedures, as I already told, that whether that is your laptop. So as if you have seen the lecture, there are class B products and class A products. Class A products are which are used in industries, and class B products are which are used in residential premises, like your laptop or your, right. Now yeah, so EMI EMC is not exactly a recent phenomena, like recent area of interest. People
Okay,
are studying this from a long time, but the point is, in laboratories they are not very extensively studied, or in
okay, ma'am.
academia I would say, because the design of EMI filters, all these things are kind of still a not very what should I say, not very articulately defined in textbooks. If you see any standard textbook, they are not they don't provide like very
Yes.
thorough data on EMI or EMC, right? I haven't seen
Yes.
at least on EMI, EMC. There are some books
Yes.
actually, but in standard textbooks, you will not get any information on EMI or EMC, or how to design EMI filters, how to mitigate the noise, all these things. Okay.
Okay.
So yeah, but if you are target if you want to design something for a commercial vehicle actually, and you want it to commercialize, you want it to go into the industry, then you will have to learn EMI and EMC. You will have to the product will have to go through all the test procedures. It will have to like EMI interference, compatibility, all these things will be tested, and if the product passes those tests, then only it can get commercialized. Otherwise, it will be discarded. That is the point.
Okay, madam.
Yeah, yeah. Yeah. So,
I
okay,
just want
then.
to
Hmm.
give a small hint actually. So
Yeah.
since very long I have completed my education, so I am not well with these calculations and other things. But yeah, I'm just trying to refresh. For these things, as he asked and you, I also work for that onboard charger, OBD, onboard
Hmm.
charger.
Okay.
And so what you have to do is like there are some in internet we can able to find what are the test procedures of TUV, CE, and EMI, EMC. So there are test centers. Even Wipro is having a test chamber.
Hmm.
TUV is having a test chamber. So if
Hmm.
you go to the site and what are the tests they are proceeding, if you
Huh.
list out what are the tests they are proceeding, then you
Huh.
will come to know what is the market standard. Because now everywhere it is like electrical vehicles are coming. As you told, like not before that electrical vehicles also, we have a CE standard, TUV, Class A, Class B, like that. So if you
Okay.
look into that test procedure there,
Mm-hmm.
and you
Mm-hmm.
relate with your subject, our subject, so it will be very helpful. So that's how I did previously.
Okay, sir. So,
Hi, Murali.
could you help
Yeah.
us with like I told I put my mail ID. So can you share some links or some reference material over there so that I can also share with the other, like the the materials which are available for general public, not any confidential item.
Yeah.
But if
Okay.
there are any useful link or reference material, please share with us, okay, so that
Okay.
other people can
Okay.
also get to know.
Yes. Yes. There are some
Yeah.
proprietary
Sorry
product
to
for my
interrupt.
company. Yeah. Yeah.
Yeah,
Tell
yeah.
me.
Yeah,
Okay, I will.
Murali. Yeah. Can you?
Actually, I
Yeah.
am also trying to learn because as I already told, I also like I wanted to learn this thing because EMI, EMC, like they are not taught in our curriculum, but these are very important aspect when you are designing an EV charger or any
Yes.
converter for the EV powertrain. So I also
Okay.
want to learn. So if you have any useful material, please share with us. Okay.
Sure. Like
Yeah. Yeah.
one more question.
Murali, can you give me your phone number?
Yeah, it's like I can give me my WhatsApp number.
Yeah.
Uh, like
Can you tell
nine
it
double
now?
zero. Yeah, nine
Nine
double
nine
zero
double zero
double eight
double eight
double one
double one
988.
900 88 11 988.
Yeah, right.
Okay. Thank you.
Yeah, sure.
My name is Ravi
Like,
Teja.
okay. You can message me so that I can find the suitable time because the time difference is 4.5 hours from India to France.
Okay. Thank you.
Okay, sure. So, like there are some proprietary documents which I can't able to share, but in the general thing, I can relate. I try to search and I'll let you know about these
Okay.
topics.
Okay.
And one thing is like, I just want to know which for the PCB designing, which tool you are using.
So usually we use KiCad or Altium.
Yeah, right. Exactly. That is what I want to. In RTM, like for that EMI EMC combines, there are some tools which we can, for example, if there is a switching device is there, you should not keep it to the sensitive unlock system and other things and all. So there also we can learn. It's there is, as you told, there is no exact topic for this, but from the tool, why the pulse transformer and all put it in the cross and isolated from the Altium side. So that is also one of the things. Everywhere we have to take it from our resources, but there is no exact curriculum for this actually.
Yeah.
That is the problem.
Yeah.
So Altium is a very good tool, for RF as well as the power sector, we can able to use that one. In that one also, if you just explore it, because it's a licensed tool, I don't have the tool. We can able to explore more why we are using this this one and all. So in the time of both the charge and discharge phenomena for the OBD charges, we can able to identify the use cases, what and all we need to be run and other things. But I try to find some videos. Yeah, tell
Are
me.
you also working on vehicle to grid aspect?
Yeah. I was working. V2G also I have worked. Yes.
Okay, thank
So
you.
do you
So
so you are so basically which kind of charger do you design, like for heavy vehicles or like two-wheelers or four-wheelers,
so like I have did it for the four-wheelers, not for the heavy
okay.
vehicles.
Okay.
But the principle is the same. The principle is the
Yeah.
same for
Yeah.
everything.
Yeah,
So
so like do you like that is for 800 volt battery system or 400 volt? What is the more popular choice nowadays?
I work for the 400 volt battery systems.
Okay. Because
But
nowadays I think 800 volt is also coming for three-phase systems, 11 kilowatt or 22 kilowatt high power
yes.
chargers.
Yes.
Yeah.
Only that the load and other management we have to take care of it.
Yeah.
So it is if you familiar with the either 400 or any one of the single phase system, it will be very easy. You should have a hands-on experience
Yeah.
so that we can able to find out how whatever the cases of charger, OBD charger, we can able to do it.
Okay, thank
Since
you.
like
Thank you.
yeah yeah
Hi, you were
yeah
saying
since
something?
since even one of previously I was working in one of the Bangalore company. There also we don't have the lab setup for the EV. So what we will do, we will just perform, everything is final. We have a lab setup, but for the testing chamber, we either will go to TUV or like there is a Brilla group of institute is there, bits. So there we will go and we'll do a test. For that we have to pay and we will make our test.
Okay. Which company did you tell you were working for?
Yeah, I worked for L&T Technology Services.
अच्छा L&T. Okay. अच्छा.
Yes. So
Okay,
okay.
nice to talk to you. Well, it's okay.
Yeah,
If you could just share those things, like it will be helpful. Okay, so
sure. I'll search and I'll let you know.
yeah, sure. Okay.
Okay.
Okay, thank you then. Then we
Okay.
will conclude today's session and next week, same time we can meet. Okay.
Okay.
Okay, thank you.
Okay, thank
Thank
you.
you all.
Thank you for joining.
Thank you.
Yeah.
Thank you all.
Piece of moisture.